everyone, and welcome. Today, we're going to tackle two really huge ideas. First up, we'll dive into the cosmic dance, the one that controls our days, our years, our seasons. Then we're going to look at this wild challenge of how you take that entire spinning planet and somehow squash it onto a flat piece of paper. So yeah, let's jump right in. It's something we take for granted, right? Every single day, the sun comes up. Every year, the seasons change. It's just the rhythm of our lives. But have you ever stopped to think about the why? What's the giant invisible engine that's making all of this happen? Well, that's what we're here for. We're going to pull back the curtain and take a look at the gears that make our world go round, literally. Okay, so let's start with the most basic, the most familiar rhythm of all. Day turning into night and night turning back into day. It's all about our planet's daily spin. All right, the first big word we need to know is rotation. And honestly, it's super simple. Just picture a spinning top. See how it spins around a central point? That's exactly what the Earth is doing. It's constantly spinning on this imaginary line that goes right through the middle, from the North Pole all the way down to the South Pole. We call that line its axis. So this spinning has a pretty huge consequence. I mean, think about it. The Earth is a giant ball, and the sun is like a giant light bulb. It can only light up one side of the ball at a time, right? Well, that line, that boundary between the bright, sunlit side and the dark, nighttime side, that has a name. It's called the circle of illumination. And as our planet spins, you and I are literally carried across that line every single day. When we cross into the light, that's sunrise. And when we cross back into the dark, that's sunset. And how long does one full spin take? Yep, you already know this one. It takes about 24 hours. That period, that one full spin, is what we call an Earth day. It is the most fundamental clock we have. It's the clock that pretty much all life on this planet is timed to. All right, so we've got the daily spin lockdown. That's day and night. Now I want you to mentally zoom out, way out, because while we're spinning like a top, we're also making a much, much bigger journey. We're talking about our planet's yearly trip through space. Now, this is super important. We have to keep these two ideas separate in our heads. On one hand, you've got rotation. That's the daily spin, causing day and night. And on the other hand, you have revolution. That's the big yearly trip around the sun that gives us our seasons. Let's dig a little deeper into what revolution is all about. So, yeah, revolution. It's just the Earth moving along a set path. We call it an orbit, all the way around the sun. And there are two really important details to catch here. First, the timing. It takes 365.25 days to make one full trip. And trust me, that little quarter of a day is a huge deal. We'll get back to that. Second, the path we take isn't a perfect circle. It's actually an ellipse, which is basically just a slightly stretched out or squashed circle. Okay, so what about that extra quarter of a day? What do we do with it? Well, for 3 years, we basically just pretend it's not there. It's just easier. But you can't ignore reality forever. After 4 years, you've got 4 of those quarter days, which, boom, adds up to one whole extra day. So to get our calendar back in sync with where the Earth actually is in space, we add that day back in. We stick it at the end of February and we call it a leap year. It's such a simple but totally brilliant fix for a cosmic headache.
But hold on a second. If we're just orbiting the sun, why do we get seasons? Shouldn't the weather be kind of the same all the time? A lot of people think it's because we get closer or farther from the sun, but that's not it. The real secret, the key ingredient to the whole thing, is a tilt.
This right here, this is the magic number. That imaginary line we talked about, the axis from pole to pole, it's not straight up and down. It's actually tilted over at an angle. And this is the most important part of the entire explanation, so listen close. As the Earth travels on its year-long journey, that tilt never changes. It stays pointed at the exact same spot in deep space. It's this constant, unwavering tilt that is the one and only reason we have seasons. Okay, let's pick a date, say June 21st. At this specific point in our orbit, the top half of the Earth, the northern hemisphere, is tilted directly toward the sun. Imagine you're shining a flashlight on a ball. If you shine it straight on, the light is bright and concentrated. That's what's happening here. The sun's rays are hitting the northern hemisphere head-on, delivering a ton of direct energy. And that gives us summer, and the longest day of the entire year. We call it the summer solstice. And this is where it gets really cool. On that exact same day, June 21st, while the North is enjoying summer, what's happening down in the southern hemisphere? Well, it's tilted away from the sun. The sunlight hits it at a really shallow angle, so the energy is all spread out and weak. And the result? It's winter. They get their shortest day and longest night of the year. Think about that. It's the same sun, the same planet on the same day, but we get completely opposite seasons, all because of that simple tilt. All right, now let's hit fast forward. We're going to travel 6 months around the sun to December 22nd. The Earth has moved, but remember, that tilt is still pointing in the exact same direction in space. But now, because of where we are in our orbit, the northern hemisphere is the half that's tilted away from the sun. So we get winter. And the southern hemisphere, it's their turn to be tilted towards the sun. This is why Christmas in Australia is a summer holiday. They're not building snowmen, they're having barbecues on the beach.
So we've got the two extremes, summer and winter. But what about the points in between? Well, twice a year, around March 21st and September 23rd, the Earth hits these sweet spots in its orbit. In these positions, the tilt is sideways to the sun. Neither the North nor the South Pole is tilted toward it. The sun shines most directly right on the equator. And on these days, something amazing happens. Day and night are almost exactly equal in length, everywhere on Earth. We call these the equinoxes, and they're what we experience as spring and autumn.
And you know what's just incredible to think about? This isn't some newfangled discovery. The ancient Indian astronomer Aryabhata was writing about the Earth being round and rotated on its axis way, way back. It just goes to show you people have been staring up at the stars and figuring out these huge cosmic truths for thousands of years. It's pretty amazing.
Okay, so we've taken this epic journey through space. We know our planet is a giant, spinning, tilted ball. Now, let's bring it all back down to Earth, because this brings us to a completely different, but just as tricky problem. How on earth do you draw a picture of a giant ball? And that right there is the single biggest headache for every mapmaker who has ever lived. I want you to try this sometime. Take an orange, peel it in one piece if you can, and then try to lay that peel perfectly flat on a table. Just try it. You can't. It's impossible. It's going to rip or stretch or tear. Well, our planet is that orange, and a flat map is that table. It's the exact same impossible problem. This is like the #1 rule of mapmaking. You can't do it perfectly. It is impossible. Every single flat map you've ever looked at, no exceptions, is a compromise. In order to turn a round globe into a flat map, you have to distort something. Either the size of the continents gets all wonky, or their shapes get stretched out, or the distances get messed up. So a map isn't a perfect picture. It's a clever, incredibly useful, but ultimately flawed solution. So if every map is flawed, how are they so incredibly useful? Well, it's because maps have their own special language. And if you can just learn the 3 basic words of this language, you can suddenly read and understand almost any map you come across. Okay, word #1 is scale. This is all about distance. The scale is basically the magic code that tells you how a small distance on the paper relates to a huge distance in the real world. You'll see it in the corner, something like 1 inch equals 1 mile. And that's how we shrink an entire country down to a single page. Now, here's a tricky part that trips people up. A large-scale map actually shows a small area, but with tons of detail, like a map of your neighborhood. A small-scale map shows a huge area, like the whole world, but with way less detail. Word #2 in the language of maps is direction. This one's pretty easy. Almost every map will have an arrow or a symbol pointing north. And once you know where north is, you can figure out everything else, right? South is opposite, and then you have east and west. We can even get more precise with points in between, like northwest or southeast. It just gives everything on the map a sense of place. And finally, word #3 is symbols. Look, you can't draw every single house and tree on a map. It would be a mess. So instead, maps use a kind of visual shorthand. We call them conventional symbols. You've seen them a million times. A squiggly blue line for a river, little triangles for mountains, a certain icon for a hospital. And the coolest part is that a lot of these symbols are internationally agreed upon. So it doesn't matter what language you speak, you can pick up a map from anywhere in the world and understand what that blue line means. So when you put it all together, you realize that maps are so much more than just tools for getting from A to B. They're actually stories. They're stories about a place. They tell you what we decided was important to include, what roads matter, where people live, how we've changed the landscape. So the next time you look at a map, even if it's just on your phone, I want you to pause for a second. Try to look past the lines and the colors and ask yourself, what story is this map trying to tell me?